Hi guys, here's our notes for 1.4 specific heat capacity. Now, what do these two images tell us about heat transfer? So our first one's a graph, our second one is a picture. So in the graph, we have different materials that are being subjected to the same amount of heat. So for example, you put them into the same oven. Now you'll notice that some are rising in temperature faster and more uh, per minute, so per unit time, than others. So some are getting hotter faster. Now, what does that have to do with our beach picture? Now, say you're on the beach, you're sitting out here, you're playing in the water, and you forgot your shoes in your car. It didn't matter before because it was morning, and the sun wasn't so hot. Now, what is going to be the most painful for you? Walking through the water for your feet, walking through the sand, or walking through the pavement. Now, we know that some things are going to be hotter than others given the same amount of heat. They're all getting heated by the sun, but we have the ocean that will be nice and cool on our feet, the sand, which will be really hot, and then the pavement, which will be blisteringly hot. Okay, so different materials will, depending on their color, but also what they're made of, will heat up in different ways. So if we're talking about absorbing water, uh, who would be the winner? Who will absorb water better? Some paper towel or a sponge? So when we're talking about absorbing, which one can take in more water without feeling too wet? Okay, so you have a puddle on the counter, you use paper towel to clean it up, or a sponge. Now, absorbing water, a sponge is going to be able to take in more water without feeling as wet. You wring out a sponge, you can probably wring out a lot more water, yet it won't drip as much, so it won't lose as much of that water. So that paper towel, as soon as you pick it up, it will probably start dripping, and that sponge probably won't drip very much. Okay, so the paper towel gives back water faster. It probably doesn't take in as much water, and it will also give it back faster than the sponge will. When we're talking of absorbing heat, who would be the winner? Wood or metal? Now think back to our water example. With our water example, it was how much, uh, which one can absorb more water without feeling too wet. Same deal. So when we're talking about a good absorber for heat, it's not which one will get hotter faster, it's which one can take in more heat without feeling too hot. So which one can absorb more heat. So will the spoon be able to take in more heat without feeling too hot, or a piece of wood? So let's say we had a wooden spoon and you were stirring some soup, and a metal spoon. Which one is going to absorb more heat? Well, it's going to be our wood. A wooden spoon would absorb more heat than a metal spoon. So a metal spoon gets hotter faster, but it only takes a little bit of heat to heat it up. So it's not good at absorbing a lot of heat, whereas wood is. So there's a difference between being a good conductor and being a good absorber of heat. So a good absorber would be like a good insulator. So it can take in lots of heat, it increases in temperature only a bit, and it holds heat for a long time. A good conductor, on the other hand, doesn't need to take in much heat in order to get hot. It can conduct heat really well. So it moves that heat, it moves into it quickly. It increases in temperature a lot, and it does not hold on to heat for very long. So it gains heat quickly, but it also loses heat quickly. So heat, Q, remember heat is represented by the variable Q, held or given off by an object depends on three different variables. So Q, our heat, depends on how much of that material you have, so its mass, what that material is actually made of, which is going to be represented by C, and how much the temperature is changing. So change in temperature. So how much heat you end up getting depends on, or give off, Depends on how much you have, what that material is, and what the change in temperature is. Now, defining these variables. So Q is your heat, measured in joules. Remember, a joule is just a unit of energy. Okay. M is your mass. Its units are kilograms. So we're going to have to make sure that we change any masses that are in grams or something else into kilograms. So our mass needs to be in kilograms. C is our specific heat capacity. It depends on the substance, and we get this value from a table, or it has to be given in the question. Okay, and its units are joules per kilogram degree Celsius. So one of the reasons why it's important to have your units in joules, because these kilograms need to end up canceling out. Okay, and our change in temperature is of course measured in degrees Celsius. Sometimes you'll see questions that have it measured in Kelvin, but remember 1 Kelvin is 1 degree Celsius, so don't get confused by that. And remember, if we're asked for like a final temperature or initial temperature, delta T just equals T2 minus T1. So second temperature minus first temperature, final minus initial every time. Okay, so taking a look at a specific heat capacity chart and talking about what these units mean. So you have this graph, or sorry, this table in your on your table sheet. So it gives you different materials and their specific heat. Now, what these units mean and what specific heat means is for every joule of heat that's added, oh, and you'll see this is kilograms Kelvin instead of Celsius, but remember it's just the same, so kilograms degrees Celsius. Okay, so for example, for aluminum, 897 joules per kilogram degree Celsius. This means that it takes 897 joules to raise 1 kilogram of aluminum 1 degree Celsius, or 1 Kelvin. So remember, same thing. So for water, it takes 4,180 joules to raise 1 kilogram of water 1 degree Celsius, right? So the higher the number, the more energy that's needed to raise its temperature. So thinking about our absorbers and conductors, water would be the best absorber on this list. Okay, it takes a lot of energy to raise a kilogram of it a degree Celsius. So you need 4,180 joules versus lead here, where you only need 130 joules to raise a kilogram of it a degree Celsius. Okay, so low specific heat capacity. So low Cs are good conductors, good heat conductors. High Cs are good insulators. Okay. So lecture example 4. How much heat is required to warm 100 grams of water from 10 degrees to 60 degrees Celsius? So how much heat, so remember givens, so how much heat, that is what we are looking for. So looking for Q, Q is heat, is required to warm 100 grams of water. So 100 grams is mass. So I can tell that from the units. Okay, so 100 grams, but I know that I need kilograms. So there are 1,000 grams in 1 kilogram. So divide by 1,000 and we get 0.1 kilograms, okay, of water. So that's going to be important because we need to know what our substance is from 10 degrees to 60 degrees. So we were at 10 degrees and we're going to 60 degrees. So here we have a T1 and T2. So we can figure out our delta T. So T2 minus T1 equals 60 minus 10 equals 50 degrees Celsius. Okay. And our equation. So Q equals MC delta T. What I see most often is people looking through their givens in their formula and then writing their formula, what they'll need. So we need a formula with Q, M, and delta T. So we'll be using Q equals MC delta T, checking to see to make sure that they have what they need. So we're looking for this. Okay, so we need M, we need delta T, which we have. Oh, what about C? Weren't given a C. We can't do this question. How are we supposed to find Q if we don't have C? Oh, remember, C we find from our table. Okay, so C, and we are going to be looking for the C of water. Okay, so for the specific heat capacity of water. So sneaking over here, and you will end up having this number memorized by the end of this. Not because you need to, just because you are going to be using water a lot. 4,180. So specific heat capacity of water is 4,180 joules per kilogram degrees Celsius. Okay, so now we have our C and we can substitute in. So Q equals MC delta T. Solving for Q, so already isolated. So my mass is 0.1 kilograms. My specific heat capacity is 4,180 joules per kilogram degree Celsius, and my change in temperature is 50 degrees Celsius. Now just take a look at our units, because this is why it's important that you have your units in kilograms for your mass. So kilograms needs to cancel out with this kilograms here. Your degrees Celsius cancels out, or reduces, sorry, with this degrees Celsius here, and you're left with units of joules, which is what you need for your Q. So if you had grams here, your kilograms and your grams and kilograms would not reduce. So you would not have the proper units. You would not end up with the proper answer. So make sure that you are changing that mass into kilograms first. It's very, very important. Okay, so calculating this answer, you get 20900 joules. Now we have to make sure we have the proper amount of sig figs. So 3 here, 4 here. Since it's multiplication, we need to go to the least amount, so 3. And we have 1, 2, 3 right now, so we're good. So our answer is Q equals 20,900 joules. When we have big numbers like this, it's usually good to change it into scientific notation. Once you start getting into like the 100,000s, I will require you to change it into scientific notation. So this would be 2.09 times 10 to the 4 joules. But this number is still small enough that it's okay. You can leave it like that. All right. So lecture example 5, we have a piece of iron thrown into a bucket. If the iron has a mass of 75 grams and 12 kilojoules of heat is released, what is the change in temperature? If the initial temperature was 75.3, what is the final temperature? So this is like an A and B question. So A, we're finding the change in temperature. B, we're finding the final temperature. So taking a look, breaking this down. So a piece of iron. So we are going to need what this is, because that's what we need to find for our C. Okay, so that's what we'll look up for C. So the iron has a mass of 750 grams. So that is our mass. We have 12 kilojoules of heat. That's our Q. And what is the change in temperature? So that is delta T that we're looking for. So our givens. So a piece of iron, C. Now we are given two things, a piece of iron thrown into a bucket of water. Now, do I need to find the C for iron or the C for water? If we look further on the question, the iron has a mass of 750 grams. Okay, so we're talking about the mass of iron, which means I need the C of iron. I'm just using that water to cool it down, but all of my Q equals MC delta T information will be for iron. Okay, so the C of iron, take a look at your graph. So blue, 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 iron right here is 450. Okay, so C is 450. 450 joules per kilogram degree Celsius. So the iron has a mass of 750 grams. And remember, we need to change that into kilograms. So divide by 1,000, and we get 0.75 kilograms. So 12 kilojoules of heat, joules are heat, so Q. So 12 kilojoules. Now, we don't want kilojoules, we want our units in joules. Okay, so there are, play our unit canceling game, do some unit analysis. So kilojoules and joules, and 1 kilojoule, there is 1,000 joules, so we will be multiplying by 1,000, not dividing by 1,000. Okay, we're used to dividing by 1,000 for like grams and stuff. A quick unit analysis shows us that, no, we will multiply by 1,000 here. Okay, so 12 times 1,000, we get 12,000 joules. And we want to find the change in temperature, so delta T. So A, what's the change in temperature? So Q equals mc delta T. Now remember, our steps for our problems are always first to do our givens, then write our equation. Next, isolate our variable if it's not isolated already. Okay, then we are going to sub into our equation. Solve, and don't forget units and sig figs at the end. Okay, so same steps every time. Do our givens, write our equation, isolate our variable, substitute in, solve, and make sure we have our units and significant figures. So solving for our variable, so looking for getting delta T alone. So divide by M and C, divide by M and C, those reduce. I'm left with delta T equals Q over MC. There, it is isolated. We can substitute our values in with our proper units. So Q is 12,000 joules divided by our mass, which is 0.75 kilograms, and also divided by our C, which is 450 joules per kilogram degree Celsius. Okay, so taking a look at our units, we have, joules reducing with joules, kilograms reducing with kilograms, dividing by a degree Celsius, or dividing by a fraction, sorry. So this is like 1 over degree Celsius. So this divided by 1 over degree Celsius. Remember, flip your numerator and denominator. You multiply by the inverse, so degree Celsius ends up moving up to the top, which is what we want. So delta T should be in degrees Celsius. Okay, so our units work out. As long as you've set up your equation correctly, your units will work out. So you do not have to check that necessarily every time. I'm just showing you that you can use your units to check. Okay, so putting this into your calculator, you're going to need to watch out with your calculator steps because I can already see some of you doing 12,000 divided by 0.75 times 450, which your calculator, if you put that in exactly as I said, will move that 450 up to the top instead of keep it on the bottom. So if you put this all into your calculator at once, make sure you are putting the bottom, that whole denominator, in brackets. I hate using brackets, so what I will usually do is 12,000 divided by 0.75, and then press the divide button again because you're also dividing by 450. So 12,000 divided by 0.75, divide by 450, and you will get the correct answer without having to use those pesky brackets. So you should be getting 35.555, so on and so forth, degree Celsius. If you're not getting that, you may have done the bracketed denominator error. Okay, so find a way that you will not mess that up. Okay, so significant figures. Taking a look, so 4, 3, and we are not going to be using C values. or significant figures, so it's a constant, so we're not going to be using them. We'll be using our measured values. So 750 grams for 3, so we need to round this to 3. Okay, so 1, 2, 3, cutting off here, take a peek over the wall, that 5 will end up rounding up. So our change in temperature is 35.6 degrees Celsius. Now, there's something in here that we did not really talk about. So heat is released. Now here's the problem. When I say that I have this much heat, 12,000 joules, I am saying that I am gaining that much heat. It is a positive number. Okay, now if heat is being released, that means I should be having negative Q. Okay, heat is being lost. So this is actually a negative number. Oh no, do we have to do our whole thing over again? No. So all this means is that this number is negative. I'm doing a negative divided by some positives. It changes our answer to be negative 35.6 degrees Celsius. What that means is that if heat is being released, that means my temperature is going down. You're releasing heat, temperature is going down. Okay, so that means this 35.6 degrees Celsius is lower. Like, so it's going, your temperature is going down 35.6 degrees Celsius. So my answer should be a negative number for a change in temperature. Why that is important is once we get to B, when I'm finding the final temperature, so looking for T2, so my change in temperature is T2 minus T1. Remember, we already have our givens, there's our equation, isolate the variable for T2, sub in and solve. Okay, so add T1 to both sides. Gets rid of that there, and we have T2 equals delta T plus T1. Now here's the problem. If we did not recognize that delta T is supposed to be negative, we're losing heat, then we would do 35.6 degrees Celsius plus our initial temperature, which was 75.3 degrees Celsius. So T1, 75.3 degrees Celsius. And we would get a larger number than what we started with. If we're losing heat, that doesn't really make any sense. The iron is getting put into some water. It's not going to get hotter. Okay, so it's going to cool down. So if you're doing things mathematically, you are going to get an incorrect answer. So our delta T is negative 35.6 plus 75.3. So our T2 is going to be the difference there. So we'll be taking 75 because that's what it was, and it's losing 35.6 degrees Celsius. Okay, so we get 39.7, sorry, it's not working anymore, degrees Celsius instead of 110.9. Okay, so it wouldn't make sense. You have a red hot piece of iron, you're putting it into water, and you end up with the temperature of your iron of 111 degrees. That does not make sense. So if we think about the context of the question, we can do it as well. So if the initial temperature was 75.3 and I'm losing this much heat, then that means I take away that 35.6 degrees Celsius, right? So two different ways to do it. One way, purely mathematical, recognizing that if heat is being released, that will be a negative heat, negative Q. And if heat is being gained, that will be a positive Q. So let's just leave a note for ourselves on our page here. Okay, so make a note. If I have positive Q, heat is gained. And if I have a negative Q, heat is released. Same thing with our change in temperature. So if I have a positive change in temperature, that means temperature rose. Negative change in temperature, your temperature fell. Okay, so don't forget to check in your question whether you should have positive and negative heat and positive and negative change in temperature. Okay, um, besides that, just double checking, making sure our significant figures are correct for this. So 3 significant figures. Well, actually, this is adding and subtracting. So 3 here, or 1, sorry, decimal place here, 1 decimal place here. So we should have 1 decimal place, so we're good. So T2 equals 39.7 degrees Celsius. So that's our final temperature. All right. You are ready for your assignment. So page 319, 3 to 5, and page 336, number 53 and 54. Just a hint for 4B. I get a lot of questions with this one. 1 liter is 1,000 centimeters cubed. You use your density to find your mass. Do unit analysis to find your mass. So play the unit canceling game. All right. That is your hint for 4B. All right. Happy assignmenting. Bye.